All right, let's move into our disk method. Now, this is disks and washers are what we're going to play around with in this section. The disk method, I think, is much better than what we've done in the first three videos. Or better. A little more straightforward, a little simpler to come up with them, and a little more likely as to what you'll see on an exam. So let's jump into the idea here. So let's say we have some sort of functions given. It's going from some point A to some point B. We have some region R. It's bounded by the x-axis. It's above the x-axis. And we need to find that, well, we'll never find that area. It's weird. We don't have to find the area. But we're going to revolve this thing about the x-axis. So if you take that area and you revolve it about the x-axis, we're going to create a volume. And we're going to want to find that volume. So let's see kind of what's happening. Let's use this. All right. So there is our function. And we start to revolve it. We begin to revolve it about the axis. You see, as we continue going, it creates some sort of solid. We get down to here, and there's some solid thing that has volume. But if you look off to the right, what's in here is it creates a circle or a disk where the radius, r, is always the function. Well, that's kind of nice because you're going to be given the function. You're going to be told what it is. So we'd have to find the area of the circle. A is equal to pi r squared. But our area function is just going to be pi times the function squared. There's our area function. And shoot, we already know from those last few sections, you're like, oh, I just have to integrate the area function from A to B, and we're going to go get ourselves the volume. Yeah, but this is already set up where you don't have to create something. It's already told to you. The disk method about the x-axis. So if you have a continuous function, where the function, let's keep it above 0 or 0. Let's not have it be negative. And then you got some closed interval from A to B. And then you're like, all right, if the region R bounded by the graph of f, the x-axis and the lines x equals a to x equals b is revolved about the x-axis, the volume of the resulting solid of revolution is, and you can read it there, pi times the function all squared, and then you take the integral from a to b. So let's see one. The disk method at work. So let R be the region bounded by the curve f of x. Hey, found it. There's f of x is equal to x plus 1 all squared. The x-axis and the lines x equals 0 and x equals 2. Find the volume of the solid of revolution obtained by revolving R about the x-axis. All right, let's do some work. So there we are. Here's our function. Cool, x plus 1 all squared. Yay. Right, some sort of parabola. If we went over on that side, it'd go like that. But we don't give a crap about that side. We're only going from 0 to 2. So we have this region here that we're going to take and revolve about the axis to where it looks something like this. It looks like some sort of horn going on there. So let's set this thing up. We say that our area function is pi times the radius squared. But our function, it's our function squared. So we take x plus 1 all squared, and we have to square it. There's our area function. But we're just going to use our formula now to say if we want to find the volume, we're going to go from A to B with 0 to 2. Okay, we're taking integral from 0 to 2. And then we need to multiply by pi times our function squared. dx. Hey, I think we're good. So let's set it up. Let's get the pi out of there. And then we're going to end up with what? X plus 1 to the 4th dx. And that's going to be our volume. Now you have some choices here. You could do a quick u sub, or you could do algebra. But I don't know about you, but I don't want to take x plus 1 to the 4th and be like, all right, so that's going to be what, x squared plus, or x to the fourth plus 6x cubed plus 6x squared. Wait a second, I have it wrong right now. Hold on. You ever seen this before? Pascal's triangle? Oh, there it is. So it's 1 times 4x cubed plus 6x squared plus 4x plus 1. Do you really want to do all that work? I don't know about you, but I really only do that when it's squared. Once it's cubed, it's too much. So why don't we do a quick u sub? Let's say u is equal to x plus 1. Therefore, du is equal to dx. So we replace our x plus 1. We call it to the 4th power. We can just put in our du, but now we need to change our bounds. Right, we're going from 0 to 2. So when x equals 2, u is equal to what? 2 plus 1 is 3. And when x is equal to 0, 0 plus 1 is 1. Cool! Now let's take care of our integral. Okie doke. All right, so it's pi times, what do we have? U to the 5th over 5, evaluated from 1 to 3. Like pi times 3 to the 5th over 5 minus 1 to the 5th over 5. And what's 3 to the 5th? 3 times 3 is 9. 3 times 9 is 27. 3 times 27 is 81. That's the 4th power. And then 3 times 81 is 243. Okay. So we have pi times 243 over 5 minus 1 over 5. So it looks like we get 242 pi's over 5. Bang! So the calculus wasn't so bad on that, but it's all about setting it up. Getting this function. Having to know that all we do is pi times the function all squared if we're going about the x-axis. Now, a lot of the trick for y'all is going to be able to figure out whether you're asked to go about the x-axis or whether you're going to be able to go about the y-axis. It's going to change up. We won't mix it up yet. The next one we're going to move into is the washer method. Washer method is pretty straightforward, not too big of a deal. And then we'll start dealing with going about the y-axis. All right.